be here. This is an unusual sort of academic talk because it's not an academic talk, right? It's an NAS briefing. And just so you understand the rules associated with, when you agree to chair an NAS committee like this, you agree to the task that they hand you, and you also agree to abide by the dissemination rules, right? And so what I'm going to give you in just a minute is a sort of one of the official briefings. I should also warn you that this will be my 50th briefing on this. all different lengths, almost all of them on Capitol Hill, where there turns out to be an enormous amount of interest in this topic on both sides of the aisle. On the Republican side of the aisle, because this is negative emissions are seen as a technology by oil and gas people as a way to extend the lifetime of oil and gas, right? Which is without having the climate implications. So, but before I jump into that, I do want to just do a little sort of announcement and commercial for a project we've just started at Princeton that we're throwing money at with both hands. And I'll only spend a little bit of time on it, but I want to introduce it just so that you know that it's there, and maybe some of you might become interested because it's bigger than we can handle, frankly. Okay, we've got a consortium that's developed. So, and it sets the context for the negative emissions report that'll follow. This first bit will be 10 minutes long, and then I'll start with one of the official sort of briefings. I've got the longest briefing that we typically give, but I'm going to skip relatively rapidly over. Some of the slides are more information dense than I would let my students do, but again, this is this is something I'm not allowed to change, right? Okay, so Bob just mentioned the wedges work, and I put this up not because I like the wedges work anymore. Frankly, when it's mentioned, it gives me a gag reflex. All right, but nonetheless, I think it's interesting because what Rob Socolow and I did in 2004, when the dominant political dodge in the decades-long game of whack-a-mole was that we don't have the technology necessary to start to solve the carbon problem, all right, in any material way. And so we thought that was simply false and wanted to show that it was false. And so we made up a game in which we extrapolated historical emissions naively over the 50 years from 2004. And then said, well, what happens if we made them flat instead? Now, flat emissions till 2054 at those levels would have carried us into 3-degree territory. So that was not a stringent target as we understand targets today. But nonetheless, you would have had to cut that green triangle out of future emissions. And that was 7 billion metric tons of carbon. That's the dominant unit people use then instead of tons of CO2. Tall and 50 years long as a triangle. And so we said, since it's 7 tall, we're going to divide it into 7 equal wedges of 1 gigaton each of averted emissions, right? 1 gigaton of averted emissions by 2050. So in total, 25 gigatons of averted emissions over 50 years in each wedge. And then ask, are there any technologies in the marketplace today, that is in 2004, that were able to handle at least one such wedge? And we identified 14. You only needed 7. Some of them could handle 2 or even 3, and so that there were multiple ways to do it. And it put the lie to the then Secretary of Energy's sort of dominant speech that we need a revolution as fundamental as the discovery of the use of electricity by Faraday in order to get started, right? But it's interesting to ask where those options are today, and so what happened. And of course, it turns out we were just terrible prognosticators. The way we sort of looked at it at the beginning is that, it was like these are Rob Socolow's slides, who's kind of a horsey guy. He likes horses, right? And so this is the beginning of a Kentucky Derby. And you can imagine each one of those horses was a different option. And so now I think many of us believe that we're sort of around the back straight. And with what we know about the climate problem now, at least the science says we need to be going to a zero-emitting energy economy in developed nations by mid-century. That's 30 years hence, all right? It's a shocking target. And so if you were to take that as correct, then we're around the back straight, and there's one turn and then a dash to the finish line. So where are the horses now? And I think it's pretty clear that wind and solar raced ahead in a way that we didn't foresee at all. They're now the cheapest forms of energy in the world in the right location, and by a lot. Onshore wind now costs less to build than it does to keep a nuclear plant that you've already paid for running, okay? And so wind and solar have really fundamentally changed this game, and their prices continue to plummet. Now, of course, those resources are variable, but nonetheless, they offer the opportunity of producing, maybe 40 or 50% of electricity with current technology at costs lower than anything we pay today. And that pays for a lot of the high-end stuff to firm up the power. So what is available on the high end? Well, at the same time that there was this revolution in wind and solar, there was also a revolution in the availability of unconventional gas. We had a gas for coal wedge. That's not good enough anymore. You'd need to do gas with CCS for coal if you wanted to firm up electrical power now. But nonetheless, the gas wasn't available then. There was this revolution in the availability of gas. So if you think about that, those three together, the gas revolution, the solar revolution, and the wind revolution, are unlike anything in any 15-year previously for at least 100 years, all right? This was amazing progress. CCS, we also actually have done a lot of CCS. I mean, it's amazing how much the world has done in total. Many tens of millions of tons have been actually done just in sort of demonstration plants. If you include EOR in this country, we do enhanced oil recovery, we do 60 million tons of injection a year. We actually know a lot about that technology now. And the costs have come down dramatically and promise to come down really dramatically in the future. But enough about that, it's a separate seminar. Also, batteries weren't even in our system, right? The batteries jumped out of cell phones and into cars. And now every major manufacturer thinks that light and medium duty transport is going to become electrified, all right? And so it's possible to actually transfer a lot of that transportation load to the grid, which is much easier to decarbonize than a mobile source. We had biofuels, which have kind of lagged. You can see they're a bit behind there. And use efficiency changed a bit. Nuclear is still, in my view, in the hunt, primarily because of Chinese experimentation, although the rest of the world has abandoned it. But the point is that there has been real change, and there's now a collection of front runners that for what's that? Yeah, we changed the rules. We changed everything's been changed. But nonetheless, so here's just the story. Wind, just over the last 10 years, decreased in cost by 69%, solar by 76%, and lithium-ion battery packs by 85%. I mean, unbelievable progress there. This is shale gas production, and you can see right around 2008, it picked up, and now it's just, this spectacular availability of gas. And so, you now can envision an end game in the US that is really pretty tightly constrained by a combination of the scientific goal, net zero for all greenhouse gases. Talk about stringent. And the timeline, 30 years, it's constrained by available technology. You can't afford to wait if you actually want to get to net zero for some other technology to be invented, because if it's not invented tomorrow, you can't deploy it at the scales necessary, right? So a grid scale battery that would allow you to do an all renewable economy has got to be available now to decarbonize the economy in time. Doesn't mean that you won't in the generation after what you put in for the first generation of a zero emitting economy. You won't change it to something else. But right now, what is the mix? It's a mix. It's an almost all electric economy fueled by wind and solar, backed by gas with CCS and nuclear with existing hydro. Electric light, heat, and cooling, electric cars and electric trucks. carbon capture and storage, or hydrogen for industrial heat, and sort of negative emissions for everything else. That's the mix we have right now. And the negative emissions would have to cover something like a gigaton of CO2, right, in the US. Maybe 500 megatons, but probably closer to a gigaton. And so it's interesting that this is what we have. If we want to actually make the 2050 endgame, this is what we'd have to build. You know, and there's not a lot of debate about this. So we decided that I spent so much time in Congress, and it was clear that some kernel of certainty would help move the debate forward, in particular if there is a shellacking of the Republican Party in 2020. All right? And so what we decided to do was just to try to hire all kinds of industry mega projects experts, and we're costing out as a single mega project build the swapping of the US energy technology for this system and for a couple of variants of it. And so there's a lot of work there, but anybody who's interested in that, please talk to me, because we're going to continue after the sort of deadline, but we need this ASAP because it will inform political platforms, I believe. Right? Okay, on to the this is Jesse Jenkins' work and a summary from Jesse Jenkins' most recent paper that shows on the horizontal axis, if the renewable market share goes from 20 to 100%, what happens to costs? There have been 30 studies of this from everybody from renewable advocates who want an all renewable economy to those that don't. And everybody concludes the same thing. When you get to 100%, electricity and energy costs you 4 times more. And so there's an equity argument about an all renewable economy that I think inevitably creeps into this debate, right? So is it okay to saddle poor people and working people who are struggling with the big bill, all right, and allow energy prices to climb to 4 times? Or is it better to firm up the renewables with the firm sources of power we have today, as long as they're not emitting, with the full understanding that that's not in itself a permanent decision. That's just a decision for the next generation, right? And I'm just going to skip this. This is a set of costs, but I don't want to go there. All right, so on to the NET study. Now, from now on, although the other stuff was on the National Academy logo slides, that was just because I couldn't figure out how to take it off, right? So that part of it was not part of the briefing. This is, all right? So you all know the difference between negative emissions and mitigation, but just to be sure that everybody's exactly on the same page, I want to say the following, right? That mitigation is about reducing the rate at which we take carbon sources from reservoirs in the earth, like geologic reservoirs where oil and gas and coal live, or ecosystems, and converting those into CO2 in the atmosphere. Mitigation reduces the rate at which humanity does that. Negative emissions are exactly the opposite. You take CO2 from the atmosphere and you put it into other compounds that are either stored, or the same compound, that are either stored beneath the surface of the earth in geologic reservoirs or in ecosystems. It's the exact undoing of combustion. And this means that mitigation and negative emissions accomplish the same thing: reduce the rate at which CO2 gets into the atmosphere, at least initially, all right? And so although negative emissions are often talked about as a way to pump down atmospheric CO2 over the long term, you should think of them as part of the mitigation toolkit from the beginning. I'll be talking about a bunch of different kinds of negative emissions here, and I'll go through those in a minute, so I'm not going to outline them now. First, I want to talk a little bit about how it is useful to talk about negative emissions, all right? And this comes from a lot of work, sort of focus group work that was done during the course of the study on arguments that resonate with different audiences. The first one, for whatever reason, is to reduce carbon pollution. You can see that's distinct from reducing carbon or climate change, even though it's almost the same thing, with the exception of, say, ocean acidification, right? But nonetheless, it works for, particularly for conservative audiences. It's the argument that was used, that together with unlocking innovation, for the so-called 45Q tax credit in the Futures Act that was passed in February 2018 by the entirely Republican-controlled House and Senate. Just as a poll, who knows what 45Q is? Yeah, it's almost no one. It's amazing. It is a subsidy passed by Republicans for carbon capture and storage that is $50 a ton, almost 3 times the current European carbon price. Highest European price in the world. They also subsidized the rest of that zero-emitting energy technology that I talked about the previous December, 2 months before. So it's a fascinating story that their command and control subsidy legislation surpasses Obama-era subsidies by a long shot, all right, by a gigantic amount. So we maybe should talk about that. But socialism. It's socialism. That's what it is. And so nonetheless, this is the carbon capture and storage. You get, if you use it for something, you get less money than if you just store it. You only get $35 if you use it, right? So they talk about reducing carbon pollution, right? Reducing climate change obviously works with people who accept the science, or at least will announce that they've accepted the science. Another big one is economic competitiveness and technological leadership. The graph on the left is an emissions diagram like the many that have come out since the IPCC AR5. This one was from UNEP. You have gigatons of CO2 equivalent emissions on the vertical axis. Those are global. And on the horizontal axis, you have time going up to 2100 from 2000. The top of the hill there, that gold line, is a business as usual emissions scenario climbing from the close to 50 gigatons today to mid-century and then shrinking a bit. The red line is what you would need to do to stay beneath 2 degrees. I think that's RCP 2.6 for those of you who are into this sort of thing. The light brown is CO2 emissions, and the dark brown are the non-CO2 greenhouse gases, primarily methane and N2O. And the thing that I want you to notice is that there is substantial brown and dark and light brown late in the century when the red line has already hit 0 and even dipped a little negative, all right? Everybody's emission scenarios have this, and the biggest cause of it are the non-CO2 greenhouse gases, the darker brown bar. It's really hard to get rid of, as most of you know, all of the agricultural methane and the agricultural N2O. We have to feed the planet. Food demand is going to double by mid-century. And so negative emissions are kind of inevitable if you want to get to net zero, as long as unless we figure out some fundamentally different way to do agriculture, all right? So how big are the negative emissions likely to be? Well, you know, if you take 2 degrees seriously, it's the sort of blue that's underneath there. Those are the negative emissions. They grow to 10 to 20 gigatons globally by mid and then the end of the century, which is an enormous market. So most of the nations of the world have committed to it, even if the current US administration hasn't. All kinds of states have, all kinds of companies have, and somebody is going to sell that stuff. And whoever owns the intellectual property is going to get rich, right? So that there's an economic argument for investing in research on NETs. And finally, there's the argument that you can control carbon pollution and climate change with a less decrease in fossil fuel use. Now, less decrease is a bizarre construct, and it's because most people on the green side object to what it's actually saying. With more fossil fuel use, right, you can actually have control carbon pollution or climate change and allow more fossil fuel use. And a good idea, a good way to think about this is for airliners. You know, airliners are really difficult to decarbonize because, you know, it takes a lot of energy to fly a plane, right? Can't run it off electricity, at least not for very far. So the dominant option for a zero-emitting airliner is cellulosic biofuels. And cellulosic biofuels are expensive, but even worse, they're land hungry. And we need arable land to grow the food we need, right, with the demand doubling. Now, if you could instead develop a negative emissions technology, and I'll show you like a direct air capture technology that was, say, $50 a ton, then by an accident of units, dollars per ton of CO2 is cents per gallon of gasoline, all right? And it's because a gallon of gasoline emits, when combusted, 10 kilograms of CO2. So $100 a ton is $1 a gallon, 100 cents a gallon, right? Nice, easy conversion to remember. So 50 cents, if you were to instead run the airliner on fossil aviation fuel, but for every gallon burned, you grab 10 kilograms from the atmosphere and put it back in a geologic reservoir, that bundle is the same as not emitting to begin with. And if you can do it for $50 a ton, that's 50 cents a gallon on top of the cost of fossil. And I'm here to tell you that you are not going to beat fossil plus 50 cents a gallon with a biofuel on price. Just not going to do it. And the externality associated with the land use is far less. And so at least in principle, when Republicans hear this, at least on Capitol Hill, they're often thinking, you know, if you could really make something like this work, you could burn all the oil on the planet in airliners eventually, right? Create a market for it, keep it going. And that makes it politically attractive. The one that you hear all the time is the final one, that is to reduce there's no E on the, should be, atmospheric CO2 after an overshoot. The bottom line there, the little graph, is the RCP 2.6 scenario, one that's Paris compliant. The atmospheric CO2 concentration, you see peaks at about 450, I think it's 454 ppm about mid-century, and then declines after 2050. And the answer is, what's the story with decline? You often hear about negative emissions as being the way to reduce the atmospheric CO2 after an overshoot, right? It's the only way to do it. And I want to make sure everybody understands that that also is not true. Although negative emissions could help you achieve really, really deep reductions, you actually don't need it for a reduction. And that's because we have natural sinks. So this is a paper by Jones et al. In 2016 in Environment Research Letters, but I used it just because everything from everybody's Earth system model predicts the same thing. But this Jones paper just has these nice little waterfall diagrams that make it quite clear. And it's for RCP 2.6. It's 6 different Earth system models that do this. The first bar there is atmospheric ppm in 2050, which is 443 there in the RCP 2.6 scenario. And in 2100, it's 418. You see you've got a decline. And then those 2 bars that I've circled, the brown one is positive. That's 83 parts per million worth of fossil fuel and land burning and land use emissions from deforestation, but negative 62 from NETs. And so the net is the difference between those 2 bars added to the atmosphere. That's in the scenario, and that's in the RCP 2.6 scenario from 2050 to 2100. And so although there is a net emission from humanity into the atmosphere this way, right? Because the NETs are smaller, and negative emissions technologies are smaller than the fossil. Nonetheless, the atmosphere declines, and the reason is that the sinks continue. So the biospheric sink is negative 20, and the ocean sink is negative 27. And this sort of continues. If you look at any one of these scenarios, fossil fuel use in them continues for centuries, right? And it's because it's difficult to eliminate it all. And so mitigation competes with NETs in any one of these scenarios for centuries. Anthropogenic emissions in these scenarios are actually positive from 2050 through 2300, net positive, despite the fact that the atmosphere declines by 75 parts per million. And that's because the natural sinks have some inertia, have some momentum, all right? So negative emissions should be thought of in your mind as just another way to do mitigation. If you want to go beyond 75 ppm of atmospheric reduction, get back to 300 or something, then NETs would be the only way to do it. But otherwise, just think of them as mitigation. Why do the sinks behave in this way? It's because disequilibrium dominates. I can describe this at length if you, well, I probably have time. What time did I start? 11, right? 10:45, then I got to keep going. Okay, so the study's motivation here was a previous Academy report that called for it. The sponsors were the DOE, NOAA, EPA, USGS, the VCON Rasmussen Foundation, Insight Labs, the NAS, the Linden Trust for Conservation. This is an unusually diverse, I think it's an unprecedentedly diverse group of funders. And as I said, it's yet another piece of information that there's a lot of sort of societal information. And what they wanted, you see underlined there, is a detailed research agenda, a granular research agenda, not a bunch of goals, but projects, right? Whoops. Okay, so there's a statement of task, which basically says that. They want a detailed research agenda. But it's important that they spell out which technologies to investigate. And specifically, deep ocean options are not on this list. All right, so this report is about terrestrial and coastal options, but not deep blue sea options. I don't know the reasons for that. Well, I can guess the reasons for that, but when they ask if you will do this, you're not allowed to say, yeah, I'll do it if you change the task. You either take the task or you don't take the task. So if you ask me, why didn't we include some deep, blue sea options, the answer is because they're not in the statement of task. There are committee members. I think we had pretty good people. We can talk about who those are. The study process, you probably know, is that you have lots and lots of meetings, you read lots and lots of papers, and you write lots and lots of drafts. And there's extremely exhaustive peer review. We had more meetings than is usual. We ran out of money and had to raise more because the subject turns out to be more complicated, more intricate than was thought. So here are the negative emissions technologies we looked at. We looked at coastal blue carbon, which is simply storing carbon in the bodies of macro plants and sediments in coastal systems. Terrestrial carbon removal and sequestration, where atmospheric carbon, is stored in terrestrial ecosystems, in vegetation and soils. You can see the oceanic option there, the coastal option, is restricted to cases in which the storage is in the same kinds of stuff. It's like honorary terrestrial systems, right? Bioenergy with carbon capture and sequestration, there's a bunch of different flavors of this, but the most common is that you burn biomass in an electricity producing turbine, capture the CO2 that comes up the smokestack, and put it into a geologic reservoir. So you get a negative emission, right, together with electricity production. There's also a fuels version of this where you pyrolyze biomass, and it makes something that looks like crude oil but smells like barbecue that you can use for a liquid fuel. And it also makes biochar, which is a relatively undecomposable material you can spread in agricultural fields, where it is alleged to, and the data indicates, it increases productivity in many systems and nitrogen use efficiency and water holding capacity and that sort of thing, and then stores the carbon in the agricultural soil. Direct air capture, machines that grab CO2 from the atmosphere and put it into a form where it's stored on or underneath the surface. Carbon mineralization, almost unexplored. It turns out that CO2 is not the bottom of the energy well, as many of you know. CO2 spontaneously reacts with some minerals and forms carbonate rocks. And some of these minerals react really rapidly with CO2, hours to days. And if you ask, within 1 kilometer of the surface of the continents, how much reactive mass is there of these kinds of rocks? The answer is there's enough at least to remove all of the CO2 from the atmosphere at least 1,000 times. And so there's this tremendous resource that hasn't been viewed as a resource that's underneath our feet. And the question is there any economical or environmentally feasible way of bringing the atmosphere to that reactive surface, or bringing the surface to the atmosphere? Right? And finally, there's geologic sequestration, which was stuck in here. I don't know why, because it's not a negative emissions technology, but it is an enabling technology necessary for BECCS. It's necessary for direct air capture, right? And some forms of carbon mineralization that are talked about now use CO2 injected into basalt domes. right? And it turns out that CO2 reacts rapidly, surprisingly rapidly, with basalt to form carbonate minerals. Okay, so we reviewed each one of these. The terrestrial carbon removal and sequestration are the most tried and true. We've got afforestation and reforestation is one of the options, the forestry option. Changes in forest management, primarily lengthening the time between harvests. And then agricultural practices like a cover crop plus no-till that leads to an increase in the amount of carbon stored in agricultural soils. The carbon backbone of an agricultural soil is an indicator of its health, so that soil conservation measures often increase the carbon in soils. You get a co-benefit. The limiting factors for these are available land. All right, we need a lot of land for our current production, and if we afforest, if we plant trees everywhere, the question is we have to plant them to do any good where there aren't any trees, and what's there? Well, it's agricultural land. And so there's a limited amount that you can actually do, and worse than that, our capacity to predict what would happen if we put a price high enough that landowners just spontaneously started to convert their agricultural land to forest. We actually don't know what would happen around the world. We do know that when there are food price spikes, people riot, violence ensues. There's a great historical literature on that. But we have very limited capacity to predict the consequences of large-scale land use change, and so it should be viewed as dangerous, right? And there are also barriers by the limited per hectare rates of carbon uptake. The soil amendments you can do to agricultural soils just don't store carbon very fast per hectare. All right, valuable, but there's a limited amount that you can do. Coastal blue carbon is much the same. You can restore wetlands and get the wetlands to store carbon for a very long period of time. Doesn't saturate eventually the way that the terrestrial options do. But the problem is, of course, that the coastal systems, however wonderful, are sort of one-dimensional, right? And there just isn't that much coastal land area. On the other hand, it is also true that we do a lot of coastal engineering anyway, and by just doing the coastal engineering projects this way versus that way, you can get them to store more carbon with no change in the incremental cost. So there's real value in learning how to do this because you can get what amounts to a zero carbon price, given that you're doing the coastal engineering anyway. Bioenergy with carbon capture and sequestration, like the rest of them, is limited by land area and also by the cost and complexity. Here you're combining a zero emissions power plant with a biomass power plant, right? And it's just a complicated system to deal with. And also, if you're going to try to put the entire negative emissions need of the world on the backs of BECCS, there just isn't enough arable land to grow the feedstock. Direct air capture, chemical processes, there's one firm that will sell you a commercial machine, but they're now it's a startup ecosystem. It's a fantastic area. Cost is still greater than economic demand. All right, the one machine that's out there, this one from Climeworks, is $600 a ton. If you believe what's out there, we're good. If you believe what's out there, some firms think that the costs are now down to around 200. Our report thinks there may be 250 right now. And our report also thinks that with decades of investment, there's a high probability, like 90%, that the price for this could be brought down to $100 a ton, all right, within a decade. So that's actually pretty good, right? That's $1 a gallon for aviation fuels to offset them, all right? So direct air capture is an interesting option because it's not fundamentally limited by land in the way that the land-hungry options are. And then carbon mineralization. There are a whole lot of varieties of this. There are a couple of places in the world where this has happened spontaneously and produced spectacular and scary results. Reactions that have started that caused the volume of an enormous amount of rock over just a century or two to expand by a factor of 4, right? And so it's amazing, right? But we know almost nothing about it. There are in situ and ex situ methods. The ex situ methods are better known. They're pretty simple. You mine and grind up rocks, which you know what it costs. And for 50 or 60 bucks a ton, if you wanted to deal with tailings piles, the likes of which humanity has never produced, and the associated water problems with them, you could in fact remove CO2 this way by just mining and grinding these kinds of minerals. In situ methods would be much less disruptive, where you inject some form of CO2, either supercritical CO2, just CO2 compressed to the density of a liquid, but still is technically a gas, right, into it. Or if you get seltzer water in there somehow, you could, in principle, get a big negative emissions going that way, but we just don't know how to do it. This area is limited by fundamental understanding, full stop. Geologic sequestration has been exhaustively studied. This is not, we broke no new ground on geologic sequestration other than to recommend some large-scale experiments with basalts. Most geologic sequestration takes place in the kinds of reservoirs you get oil and gas from, which are saline aquifers where you inject it in as a supercritical fluid. As I said, even just in the United States, we're doing about 60 million tons of this year alone. And so this is already big business. There's this $50 a ton carbon price that the Republicans put on to subsidize the activity. Yeah, this is at a completely different stage, and it's just an enabling technology. So our group thought that 4 of these NETs were ready. Enough was known for large-scale deployment: afforestation, reforestation, changes in forest management, uptake and storage by agricultural soils, and BECCS. Coastal is arguable, but it was small in the overall budget. Additional research we thought was likely to further reduce costs and increase efficiency and then reduce unwanted impacts. We also see real potential for economical direct air capture. And as you'll see, we recommend sort of a crash program to try to develop it, right, that engages public-private partnerships. Carbon mineralization is currently limited by a lack of fundamental understanding, and there needs to be accelerated study primarily by universities and national labs, at least initially. Blue carbon has capacity that's less than other options, but we recommend actually a substantial research investment in it because of the potentially very low per ton costs, given that you have to do coastal engineering anyway. This number that's circled is what we think is globally available if you got complete uptake by landowners to incentives. We were talking about this earlier, right? Globally, there's maybe 10 gigatons per year worth from the land-hungry options: afforestation, reforestation, changed forest management, agricultural soils, and BECCS. These are what we think of as safe upper bounds. Safe means without some sort of unpredictable land use stampede that would disrupt our food supply and whose consequences we don't really understand. But we actually don't think those numbers are achievable because getting landowners to respond to economic incentives doesn't have a track record that inspires confidence. You might think about dividing those numbers by 2. In the United States, notice we've got 1 gigaton of capacity to divide that by 2, maybe 500 megatons. So we recommend that we have a substantial research initiative in all of these areas, but that are targeting different stages. Improving the options that are ready to deploy, rapid progress, crash program on direct air capture, and advance fundamental understanding for the others. The research here is staged. If you look at the report, every congressperson adds up all of the items and gets a total cost, and that's not the right thing to do, because the research is typically staged, where there are 4 stages, and you only do the second stage if you pass the first stage, and only the third stage if you pass the second stage. So they wouldn't be done simultaneously, and you wouldn't do the later stages at all if you didn't get a payoff from the first stages. So that's what this slide is designed. You're not supposed to be able to read this. We have 50 separate research projects, okay, and an identified sponsor, and a governance structure, and a time, and that sort of thing. And this is because there's interest in the government to actually enact some of these things, and they've already done several of them. All right, there's a new bill actually pending for the direct air capture program called the Use It Bill, introduced by Senator Barrasso, oil and gas guy from Wyoming, and Whitehouse, the liberal senator from Rhode Island. And there's also a companion bill that the House Climate Solutions Caucus is putting together, which is also a bipartisan bill. Okay, so let me get to the end here. There are, as I said, the research is staged. Most of it's designed to pay off within 10 years. Some of the research, a lot of it would be done by the academy and by national labs, but the most expensive items primarily by, you can think of them as public-private partnerships. The thing that's worked with solar and wind, for instance, and also with unconventional gas, is the government subsidized a market that then allowed firms to compete on price. And so with direct air capture, the problem is price right now. There's an enormous universe of possible recipes and physical configurations for these machines. It needs to be explored, and the price needs to come down. And so the tried and true method is to get a market going and let a whole bunch of startups compete for the market that's made possible because of the price support initially to bring it down. And so, of course, that's what we in fact recommend. There are a few frontier research projects that wouldn't pay off for 20 years or so. One of the most critical, we believe, is a 20-year investment to try to produce agricultural crops designed not just for productivity of food, but also to increase the carbon in the soils beneath them. So a lot of interesting possibilities there. I'm kind of running out of time here, so I've got a bunch of highlights. There are a bunch of unusual ones. One of them that is kind of interesting is that if we changed our recycling ethic and separated out wood products and threw it in a landfill where the stuff was designed never to decompose, all right, which is the opposite, nothing biodegradable, and if we maximized the one-time use of those products, turns out you can get 10 gigatons a year out of that, all right, really pretty interesting. It's the opposite of the environmental ethic that has been around, but it's possible actually to do without changing the biomass of existing forests, just harvesting the regrowth of the world's secondary forests and using it in this way. All right, there's a big program for the development of the new agricultural varieties. And there's also a big program to try to improve our capacity to predict the far-field consequences of large-scale land use change that would be induced by price supports for the use of land for negative emissions. These are all necessary to put in here, but there's no way for me to describe them all unless somebody asks specific questions. But we have specific programs in BECCS, in direct air capture, and carbon mineralization, and in geologic storage of carbon dioxide. Again, the rationale that we offer to all in government are that states, local governments, corporations, and countries now plan to make large investments in negative emissions technologies. And so advances in the US, even if the US federal government doesn't, will create jobs and benefit the US economy, especially if the intellectual property is held by companies here. So unlike the other mitigation options that have been spectacularly successful, particularly wind and solar and unconventional natural gas, NETs have not yet received the public investment consistent with the scale of the opportunity. So thank you, and I think I'm in time for a few questions. I'm glad you brought that up. And of course, you have to reforest in a place where it's less likely to burn, right? I mean, the way to think about a forest fire is, from the planet's point of view, all right, what matters is that when we implement some action on a landscape, that the average mass of carbon stored on the landscape goes up. All right, and that average could be a spatial average, so that, for instance, building a harvested forest mosaic where you had patches at different ages of harvest in a place that used to be pasture land, all right, means that you have trees equal to sort of the average amount of biomass through the rotation cycle there at equilibrium, right? And that means that even though you're harvesting every bit of carbon that was produced by those forests and using it, still there was a transfer from the atmosphere to the land surface because those trees weigh something that are there, right? Right? And it's the average amount. Same is true with the fire cycle through time, right? This time averaging is what you want to do there. And so burning is bad, but it's not fatal to the operation, okay? You want the least burning you can do. That's the first point. Second point, people commonly misunderstand, politicians in particular, that when allowable emissions are calculated, so the statement that we need to go to net zero by mid-century, when that's calculated, like I showed you in that Jones et al. Paper, that's already accounting for the actions of the biosphere to the extent that we can, the biosphere sink. Remember, the biosphere sink was there, and when you look at allowable emissions, those are calculated against the backdrop of the oceanic and terrestrial sinks. And so if you include the terrestrial sink that was inadvertent, like the big sink in our eastern deciduous forests, in your national budget, you're double counting. And you're not doing enough share because, right, you get the idea there? And so forest fire cycling in natural forests, not created as a mitigation project, are already included in the calculation about how much we need to do. So the GFDL model, for instance, has a big global fire model, and it may be inaccurate, all right, but there's an attempt to account for it and keep it sort of outside the anthropogenic budget. And then I'll give you Paul.
So this sounds pretty optimistic the ability to actually keep warming above under 2 degrees without resorting to the other half of this, which is geoengineering. And so you also mentioned that fossil fuel companies like this because it lets them continue to sell their product for a while. And I know you also said you're not a very good predictor based on what you did before, but give us your best prediction anyway of how successful this is going to be. First, in terms of actually funding the research, and second, in terms of the carbon capture working.
So I'm actually pretty bullish on the funding, and it's because the briefing at the DOE caused them to release a big dollop of money immediately, and because this Use It Act is likely to make it through Congress. So there's a lot of interest in this, and it's got bipartisan support as a program. So I think that we'll get research funding. I also think we're going to get some deployment because, again, it's the Republicans that put the subsidy on, and what they want to know now when you talk to them is how much subsidy do we need to really get a market going for DAC. And the answer is there may already be some of it, right? So in California, they amended the renewable fuel standard to allow direct air capture plus fossil. And that's $160 a ton subsidy already. And the Use It rule modifies 45Q so that you can collect that on top. So it's 50 plus 160, that's 210. That's about what our estimates are now. Might be enough to get a market going. So I think we're going to do some of this. Now, whether or not the country decides to go from last to first and just start building a zero emitting energy system on the rotation of our capital stock, I don't know. But I think we have a chance in the aftermath of the 2020 election, depending on how it comes out. And so I want to be ready in case the stars line up. Am I optimistic? No, I'm not optimistic about anything. But the only way to win eventually is to be ready when the opportunity arises. Those last remarks were not part of an NAS. Yeah. Paul. Yeah, that's right. Well, we did, of course, have a big investment there. We had all the, all these $25 million centers. Well, we definitely do. If you look at the whole enchilada budget, it's up there, right? But at the same time, Paul, there is a difference between the particularly the direct air capture problem and the Manhattan Project. There are only a couple of ways to build a fission bomb. In fact, that there were two, right? Yeah, and they did them both. If you ask, what is the number of possible ways to do direct air capture? It is an enormously diverse space. And if you model the properties of materials that would make it truly inexpensive, and then ask, in this same space, is this a dense region of materials, or are you like some way out la-la land where there are no current materials? The answer is it's a dense region of space. And so this is the sort of problem in which an Edisonian effort by many, 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 many independent players competing over cost has worked in the past. So it's true that national labs have been really important in making sort of efficiency advances in wind and solar. But the primary cost buy down was the marketplace.
Yeah, sure. So once you have the technology, the marketplace makes I mean, what do you do? Creating an intellectual route that can be commercial.
Mm-hmm.
So that's absolutely. That's why we have nuclear power. Mm-hmm. They're not run by the Department of Energy. They're independent from the Department. But you would never have made nuclear power plants if you didn't have an understanding of the processes that allow you to.
No, that's true. That's true. Yeah, so we recommend a big DOE program, but I think I actually think that the chemistry here is already well enough understood that we also need a startup ecosystem sort of immediately, right? For those of you who aren't inside the tent on this, David Keith is a guy from Harvard who has a company called Carbon Engineering. He's just signed an agreement with Occidental Petroleum to produce liquid fuels from captured CO2. Sounds like crazy land for me. We could discuss why, but the point is there is a going venture there finally. He built a pilot plant some 10 years ago. Peter Eisenberger has a company, is part of a company called Global Thermostat. He and his wife, Graciela Chicheninsky, are in Colombia. It's an amazing story. We don't want to go into it because I don't want to get sued. But the Columbia University, but it's an extremely interesting technology. If you ever want a seminar, there's a guy named Chris Jones who's a chemical engineer from Georgia Tech, who was actually dean of research or something there. But he's a nothing but the facts kind of character, and I think he's sort of the brains behind that operation. And then the final one is Climeworks, which is in Switzerland, and they're methodically, in Swiss fashion, marching down the price curve. Their next machine, they say, is going to be at around 300, and then 150, and then so they're marching it down. But we need another at least a dozen, and ideally 100.
So when I was on the National Academy Review last time, I was really supporting capturing the carbon dioxide of the stack gases and generating electricity. It reduces the efficiency by about 20% of the overall, but it's a much, much more condensed gas and much easier to capture. We know how to do it.
Yeah, we should do that anyway. Yeah, for those of you who are into this, right? The difference between flue gas capture, where if it's a natural gas plant, CO2 is 5% of the flue gas stream, it's 10% if it's coal. So it's concentrated relatively. And direct air capture, where it's 0.04%, right, of the atmosphere is CO2. You know, inherently you'd think, well, it's got to be way more expensive to capture it from the dilute source. I mean, just, you know, it's got to be. But there's a funny thing, right? It's the difference between a cleanup problem and an extraction problem. You've got to capture like 90% at least of the CO2 in the flue gas. But you don't have any such requirement for CO2 air extraction. You can just sort of take a little bit out as the air blows by. And so that difference actually favors direct air capture costs. And that's the primary reason why it looks like direct air capture, you know, if you had to guess, $100 a ton is a reasonable number. But CCS from flue gas is probably already at about 40. And there's a company called Net Power in Houston, look it up on the web, an alum cycle, ALLAM, that they currently have a 50 megawatt power plant running in Houston, started it up in July. It's like a big demonstration plant. Next one is a full-size commercial that emits nothing and captures the CO2 for free. All right. So it's a power plant without a stack, right? And it's definitely cool. Tony.
My question was, of all the different pathways that you talked about today, which ones do you think have the greatest uncertainty in terms of their scalability?
Well, carbon mineralization, all right? Carbon mineralization is the kind of technology you would use to terraform a planet, okay? You would terraform Venus, right, that way. So the scalability is like, you know, mind-blowing, but we have no idea how to do it, how to access the reactive capacity. So it's a pretty easy question. DAC is sort of second. It's quite possible that a search for the killer sorbent will come up empty, right? And if it does, they're never going to scale. Right? Yes, there is. So artificial photosynthesis, where you use photochemistry to make a fuel, all right, from CO2 by driving it up the energy hill, is in fact an area that Paul mentioned earlier that was invested in by the DOE in the sort of previous round of enthusiasm on this. And of course, photosynthesis itself is the engine of the four options that we concluded were ready for deployment. Right. Yeah, so you'd use it for CO2 from flue gas, for instance, right, and concentrate it, and then drive it uphill. But there are a whole variety of ways to do artificial photosynthesis, to use photons basically to do catalysis. One of the most efficient early on looks like it's going to be electrocatalysis, where you use electricity together with a catalyst to drive CO2 uphill into a fuel, usually into a 2-carbon, right, organic molecule. And you use solar electricity from photovoltaics for that. And that's kind of a plant, right? Right? So I should say that one of the main lessons from photosynthesis is photosynthesis is, in my view, one of the least well-designed of the Earth's systems. And I use it in my classes as evidence of unintelligent design. Designs that are constrained by history so that we're stuck on what is probably a local optimum. Photosynthesis, of course, was designed with an enzyme that runs backwards in the presence of oxygen, which is produced by the by the same process. It's like an engineer would never do that. You build a system not just that is quenched by what the system produces, but that runs the wrong way and then does the work. All right, and so this is what happened in nature, and it's probable that's one of the things that gives me hope about it, about artificial photosynthesis. So one of the things that they do, for instance, is study oxides a lot because they weren't available when photosynthesis evolved. Go ahead, go ahead. It's been locally perfect. It was locally perfected for a non-oxygen containing atmosphere, and then all of a sudden the oxygen overwhelmed the physical buffers. And there you were with a whole bunch of cofactors all necessary, and there was no, when it first came in, it had to be better than nothing. After the oxygen came in and squished everything, you had to have something that came in better than something that was on a locally optimal hill. Much harder problem, right? It's the constraint from the past that makes evolution a bad designer sometimes. Yes. So on the land demand side, there are tables in that report on land demand, and DAC and mineralization would be far less demanding of land, a couple orders of magnitude less than. You still need a lot of room for solar panels, right? But it's small relative to. I think you can get 25 terawatts of solar energy out of an area the size of Kansas. Now that's not chopped liver, but that's like the whole globe, right? Solar panels are really pretty good. And so we actually did care a lot about. So when the report takes, in my view, the land use constraint seriously and the multiple claims on that land, much more so than previous reports. We really took pains to do that because the IPCC has been, I think, justifiably, the integrated assessment modeling in the AR5 has been justifiably criticized for blithely assuming that humanity would tolerate tenfold increases in food prices, for instance. The most recent TNC inspired study that came out in the Proceedings of the National Academy by Griscom et al. in October, I think, of 2017, right? I think it's 2017, maybe 2018, I can't remember, is the one that people quote most of the time now. They say there's 10 gigatons of reforestation and afforestation possible. And if you look into the bowels of the Griscom et al. Study, that is all of the pasture land that they assume is going to become available because the species is going to become vegetarian. Now, I think it would be a good thing if the species became vegetarian, but good luck getting people to do it, right? So we really cared a lot about these land use constraints, tried to avoid wishful thinking, because if you get it wrong, what suffers? What suffers are food prices, and that hurts poor people. And what also suffers is wildlife. You cut down the rainforest for the land to meet the displaced demand. So we worried a lot about that. You had another question too, though? Oh, right, yeah. Yeah, there's a separate NAS report released at the same time on carbon capture and use that is all about those sorts of technologies. I've been fascinated by them. You've got some real interest and expertise in companies that have come out of Rutgers here, right? And I think it's a fantastic area, but no one thinks that it's that you can, we just have so much CO2 we make as a species. All right, it's beyond any conceivable demand. It's on the order of the scale of the earth moving of humanity. All right, when you think of of 50 billion metric tons of something. That's the same as 50 cubic kilometers of water. And if you ask what's total Earth moving by the world, it's less than that. All right? It's a huge amount of material. You don't think about that when you're driving your car, that the gasoline that you put in it, even though it's heavy enough that you'd have trouble lifting it, the amount of CO2 that's coming out of the tailpipe weighs 3 times as much. Right? Yes? Yeah, so for organic waste, what we propose. Yeah, so what we do for BECCS, because I think we're going to need some BECCS, frankly, and we propose using the organic waste of the world in BECCS, and that includes primarily the forest and agricultural residues, but it also includes municipal waste because there's a lot of it. And so if you could design a program that captured a large fraction of humanity's waste biomass and then burned it, captured the CO2 and put it below ground, that's maybe $50 a ton. And you take care of the biomass problem, the organic biomass problem, and you get electricity, and you get a negative emission. Yes. It's fossil. Thank you all.